Beta 1, the Triton Paradox. Now you will hear two pairs of sounds. Listen and determine whether the tone in each pair is rising or falling. Pay attention, and the correct answer turns out differently for everyone. Some hear an increase, some hear a decrease. Let me know in the comments what's yours. We'll have a showdown. Well, this sonic illusion is called the Newt paradox, and the trick here is that from a mathematical point of view, the tone neither goes up nor down, but remains the same. What a twist! The explanation is quite interesting. The point is that every sound you've heard is what's called a shepherd tone. It consists of several sine waves, the frequency of which is obtained by multiplying by 2, so for example 55 Hz, 110, 220, 440, 880, 1760, and so on. In other words, it's the same note taken in all octaves at once. The only thing is that the volume of all the notes is different, so the lows and highs sound quiet and the middle sounds loud. So it turns out that each shepherd tone has a specific note, but there's no specific frequency. It's a whole spectrum. And now look. If we play two shepherd tones in a row, shifted by half an octave, this is a tritone. We will get our paradox, tritone. The note will be obviously different, but it will be higher or lower. You can't determine it unambiguously. After all, the new sound will have both higher and lower frequencies. The frequency does not change at all across the spectrum, but paradoxically we can clearly hear either a rise or a fall. If we try to understand why this happens, we need to go deeper into the human perception of sound. So there's no clear explanation. But what is interesting is that there is a study that found that what a person hears depends on their language, dialect, and even country of residence. Yes, not very tolerant, but it is a fact. In such subtle things, we are really different. By the way, I said that this paradox is like a Necker cube, only for the ears. Actually, it is a cube drawn on a plane, the orientation of which depends only on our perception, either the back wall or the front wall. If you practice, you will be able to hear both ways with Triton's paradox. For example, after playing pure tones. In the first case, you can hear a lowering, and in the second case, an increase, even though it's the same sound. And while we're on the subject, I absolutely love shepherd's row. If you turn on a shepherd tone and smoothly raise its note, and then turn on another one, another one, another one, another one, and so on, then it will seem like the sound is constantly rising, but it goes on endlessly. Listen for yourself. I'll leave a link to the looped track in the description. The secret here is quite simple. Since each shepherd tone has a wide range of frequencies, they smoothly, imperceptibly change each other in the process. But the effect is certainly impressive. If you want to drive someone crazy, now you know what to put on. 2. Wigner's friend. Well, wait a minute. What about the cats? Schrodinger's cats. You're probably familiar with this truly confusing thought experiment. But it turns out there's an extended version of it involving one more person. It's called the Wigner's friend paradox, and it can really break your brain. But first things first, let me remind you that the paradox of Schrodinger's cat boils down to the fact that the very fact of our observation radically changes its state. While the box is closed, the cat is both alive and dead. But as soon as we open the lid, he instantly jumps into a particular state. And exactly how this happens is a big mystery. It's already complicated, yes, but Hungarian physicist Eugene Wigner apparently thought it wasn't complicated enough and added something else, a friend who is in another room behind the door. And at first the same thing happens. You open the box, you see, for example, a live cat, and for you its transition from the state of superposition to the ordinary state takes place. But your friend does not know the result of the experiment yet, and it turns out that for him, the cat is still alive and dead. Then the question arises, in what state is the cat now? What is the objective reality? And does it even exist? And even when a friend finds out that the cat is alive, his friends will not know. And what it turns out, until the whole world does not know the state of the cat, he will be both alive and dead at the same time in the scale of the universe. It's a mess. Is everything around us in some indefinite state? Alas, there is no explanation for this paradox. We can offer only interpretations, but they look the least discouraging. The most disconcerting explanation is the many worlds interpretation. According to it, the observer enters an entangled state with the cat, or rather with two of its states. Accordingly, his friend does too, and two versions of the world arise, in each of which the cat has a quite specific state, the same for all. It is just that for some time the observer and the friend do not know in which version of themselves they find themselves, but the important thing is that reality is the same for them. In this case, we have to assume that there are all variants of outcomes of all events, and where they fit in space, why they do not interfere with each other. It is not clear. So the many worlds interpretation, though good, does not suit everyone. The Copenhagen interpretation is also popular, but it doesn't get better. There, everything depends on whose point of view to look at, and it doesn't give an unambiguous answer about the cat's condition. However, there is hope for relatively new interpretations that are not yet so widespread. For example, relational quantum mechanics. In it is impossible to describe objects without an observer, because some relation is postulated between him and quantum system, and with each observer this relation is different. So it turns out for someone the cat is alive, and for someone else, alive and dead, or quantum Bayesianism. There it is directly assumed that objective reality does not exist, and quantum theory describes unreal physical objects, but the expectations of an agent when interacting with them. It allows us to calculate what we will detect in an experiment with what probability, what values, but in itself there is no real world, and everything we get in measurements is an illusion. Well, since it may be different for everyone. There are other interpretations that offer even more unusual concepts, but all of them in one way or another boil down to one thing: to explain quantum physics and to solve some paradoxes we have to sacrifice something. Localization of the theory, existence of only one world, independence of the observer, or even objective reality in general. This is the price we have to pay, and we have no other options, even if someday an interpretation will be found that easily explains all the oddities of quantum physics. In it, we will have to give up many familiar things. 3. The Mpemba effect. We continue with the paradoxes. We take two containers, one with cold water and one with hot water. We put them in the freezer and wait. Here's a question: which one will freeze faster? Yes, of course, I couldn't get past Mpemba's paradox. In 1963, a schoolboy from Tanganyika in Central Africa discovered that a hot ice cream mixture freezes faster than a cold one. Together with physics professor Dennis Osborne, he conducted more precise experiments, and this was confirmed, even for ordinary water. Even though the hot sample still has to be brought to the temperature of the cold one, it still turns to ice faster. As only tried to explain this incredible effect, and the fact that the hot container melts frozen ice in direct contact with the surface, and that hot water evaporates more strongly and it remains less, and that it has more dissolved gases and there are bubbles that accelerate heat exchange, and that on cold water grows only ice and prevents cooling, and hot water freezes at the bottom and walls. Even hydrogen bonds have been considered, which disappear in hot water, and no energy is spent on their destruction. However, there is still no unambiguous answer as to why this happens. It turns out that there are so many subtle details in this simple experiment that it is extremely difficult to account for all the mixed variables and determine what exactly affects the result. In addition, this paradoxical effect does not always occur. One condition is rapid cooling, but in this case, the container with water becomes a non-equilibrium system. Different parts of it will have different temperatures, the slightest shift of sensors, and the value can change a lot. So maybe the Mpemba effect doesn't exist at all, and all these strange results are the work of Satan, or even simpler, errors or errors of experiment. However, as long as there is not found any frank obstacles why hot water cannot freeze faster than cold water, this paradox is not considered as some marginal or anti-scientific. So many scientists do not give up trying to understand it. The simplicity of this experiment is too much of a payoff. In addition, in the course of research, manages to find new phenomena and subtleties of the structure of thermodynamically non-equilibrium systems. So maybe it is even good that this question still remains unsolved.